Okay, we're looking at cell potential and free energy here. So we first need to go through what cell potential is, and then we need to see its connection to free energy. So remember, we have our normal cell. These are not going to be the electrolytic cells. These are going to be the voltaic cells. So cell potential, difference in potential energy between the anode and cathode. It really depends on how easy the oxidizing agent is reduced and the reducing agent is oxidized. We see this as E with the standard for the cell. Standard conditions, 25 Celsius, atmosphere for gases, which is pretty rare, but does occur, and 1 molar concentration. You really add the cell potentials for each half reaction like I showed in 9.6 with coupled reactions. So where this comes from, the standard reduction potential, we can't measure the absolute tendency of a half reaction only relative to another. This is kind of like what we have for delta H, delta S, delta G. We need to see the change rather than just having the actual amount. So it was selected at some point that the standard half reaction reduction of hydrogen ion to to hydrogen gas under standard condition, they would assign a 0. Totally arbitrary. You could see it's a She, standard hydrogen electrode. So this is just what was done in order to say if we call this 0, then everything else we compare this to will be some kind of voltage, and then we can use that concept when we add and subtract them because they all come from the same comparison of the standard hydrogen electrode. So it's defined exactly to be 0, again under standard conditions. So half reactions with a stronger tendency toward reduction have a positive value. Half reactions stronger tendency towards oxidation, negative value. Because remember, oxidation is going to be when they lose electrons. So thinking of that, oxidation negative, because negative electrons. So for an oxidation half reaction, its amount is negative of the reduction. That makes sense because the opposite of oxidation is reduction. And so if we negative it, I can't think of a word, then we'll be able to say that they're the same value. So we have this reduction table. There's a nice one in the book. That's why I got this one. You can find others online. Again, they might have slightly different values. But again, we want to see that the stronger oxidizing agent, which means that it's strongly reduced. So these are strongly reduced, which is why their voltages are very high. Weaker reducing agent. That makes sense again. While the other hand side is true. And so if we need to flip the reaction, we need to flip the sign. So the idea that this going from an ion and being reduced as negative 0.036, if we went from the metal to the ion, it'd be positive 0.036. So we got to keep an eye on what's going on with each of these and be aware that different ions have different amounts. So this one's like 3 plus. This one's also 3 plus, but this is losing 1 electron, not losing 3. So that reduction of 3 to 2 is actually a pretty good voltage compared to 3 to nothing. So keep an eye out for the exact ideas here. But again, if you're on the AP test, they're going to tell you these. They're not just going to give you an open table this large and say, choose your, pick your poison here. Now, if you multiply a reaction, don't multiply E. So if we multiply this times 2, it doesn't become 2 times this. This is what's called a state function and does not change based on quantity. So be cautious of that. So some example here. Which reaction is more likely to happen at the cathode? Which one's happening at the anode? So the cathode has the greater reduction, more positive. Anode, oxidation, loss of electrons, more negative, or you could say less positive. Because that's going to be often the case, is you're going to see ones that are going to be both positive. So the more positive one is going to be your reduction, cathode. Okay, you want to make sure you get those straightened. So we really want to make sure we understand which we have this here. And likewise, if we had to have this on the opposite side, we would have to switch that around and that would be negative 1.5. So let's take a look. When we think of the electron or the voltage for the cell, this is the oxidation plus the reduction. when looking up the values on the reduction table, flip the sign for the one that's being oxidized, because you have the opposite reduction taking place compared to what's written on the chart. So this can easily be confused. And when they give it to you on the AP test, they're not going to necessarily give it to you in the right direction. Okay? They're not going to give it to you in the right way. When adding these electron values, I can't want to say electron, energy values for the half cells, don't multiply the values, even if you need to multiply the half reactions to balance the equation. So let's take a look. So, what's the cell potential for a cell made with silver and gold? That's the same one we had before. Because this one is the higher one, it is the cathode, more positive. So the higher one is going to be the positive one. The lower one's going to become negative. So that's an easy way to remember it. The higher one is more positive, therefore is going to be positive. The other one is going to be negative because it's less positive. Okay? So we had to flip the sign for the silver reaction. Right? You can see we flipped it from, in this case up here, it's reducing. We want to have it oxidized. And we need to see that we need to multiply these times 3 in order to balance the reaction, but we don't multiply anything times the values. We're just going to add them together. So you might have part of a FRQ where you need to balance the reaction. So you do. That's not too hard here. On the other hand, you're going to need to not do that when it asks you for the voltage. So the cathode plus the anode, and again, you can see it's the negative part of it to get 0.07 volts, 0.70 volts. So when we're looking at that table of standard reduction potentials, the redox reaction will be spontaneous when there's a strong tendency for the oxidizing agent to be reduced, reducing agent to be oxidized. So let's take a look back at that list here. So these are strong oxidizing agents that are going to get reduced. These are strong reducing agents that are going to get oxidized. So what that's saying is that if we got something up here paired with something down here, oh man, that's going to create some really good voltage. Because again, the higher one on the list is going to be positive, so it stays as is. The lower one on the list is going to be flipped negative. So positive minus a negative is going to be a positive, and we add them together. So we want something up here and something down here to get a voltage, okay? But keep that in mind that that's what we need in order for us to have a good cell potential. So an example from the reduction potentials, we have these two given, right? Copper is more positive, so it's going to be reduced. And we can see it's going to stay this way, right? Going to go from the positive to the 0. Zinc is going to be negative, more negative, so it's oxidized. We need to flip the equation and sign for energy on zinc. And we can see that these are going to be canceling out. We got our zinc becoming zinc 2 plus, copper 2 plus becoming this. We're going to add them together. We get a 1.1 volt value. Because this is positive, it's spontaneous, which means delta G is negative. So this is for a common galvanic cell. Let's look at an electrolytic cell. So that means the energy of the potential is negative. Non-spontaneous delta G is positive, which makes sense. It's not going to run itself. This cell's undergoing a reaction, okay, given as is. Careful, this is telling you that Na is going from a plus to not 0. It's being reduced even though the table shows it would rather be oxidized. And chlorine is going from a negative and being up, so it's oxidized, even though it'd rather be reduced. So we have our values, right? Positive for the reduction, negative for the oxidation. We need to look at which one's more positive, more negative. So in this case, remember, this is telling us what's being reduced and oxidized. So we need to flip the sign in order to get there. And again, this chlorine should be down here. Got mess up in the order. So the idea is that this chlorine's down here with these electrons producing the 2 chloride ions, while this is just the ion like we have up top. So these are both negative. We add them together. And so this will need 4 volts in order to produce and run this cell, which makes sense. That would make sense that you need to have energy to run this type of cell. So here's our little diagram that's going to really put it all together. So we have the connection of Gibbs free energy and equilibrium, the electrolytic cell and equilibrium, and the electrolytic cell and delta G. So this is going to be used, as you can tell, many, many different ways. That's what we're going to be looking over the next few sections here. Let's take a look first. So between the cell, Gibbs, and equilibrium, for it to be spontaneous, again, one that goes in the forward direction with the chemicals in standard states, delta G is negative, E is positive, it has a voltage, and K is greater than 1. Now, when we put these all together, N is the number of electrons. Those are the number of electrons in your balanced equation. That's where those are pretty essential. Then you have Faraday's constant, this kind of funky value. It's so many charges per mole. Again, we'll talk about that in a further, I think it's the next one. You often see it as 96,500. Follow whatever is on the AP periodic table or reference sheet, because that's the value they're going to use going forward. So if we are calculating delta G for a cell, we have the number of electrons in the balanced redox reaction, Faraday's constant, and then the electrolytic voltage. So we can see that 2 electrons are being transferred. That's pretty simple to see. So that's why I have 2 moles of electron. The 96,485 coulombs per mole. You can see those cancel out. And volts are joules per coulomb. That's energy per charge. So we can see our things all cancel out. We're left with so many joules. We can see this is a negative delta G, which means it is spontaneous. We would also know it to be spontaneous because this is positive. So keep in mind, we've got all these different things, but we could solve for N, we could solve for E. All of these are connecting. We can solve for any one of these areas. But again, you also need to understand what part or where we use these, so you understand what kind of connection there is. Recognition is going to be half of the battle. The other half is doing the calculation, which again, we're just multiplying, dividing, adding, and subtracting. Nothing too crazy. And again, you'd have your scientific calculator to help you out. All right. We're going to continue to look at this in the next section. Take care. Let me know what kind of questions you have.